Ambient noise is a physical event. Sound travels as a longitudinal pressure wave, moving through air in alternating bands of high-pressure compression and low-pressure rarefaction. Active noise control relies on the principle of superposition. When two of these acoustic waves overlap in the same physical space, their displacements combine to form a new waveform. To create silence, a system must generate a secondary wave that matches the incoming noise in frequency and amplitude, but with a precise 180-degree phase shift. This is a race against the speed of sound. A microprocessor must detect the incoming wave, calculate its inverse, and drive a speaker to project anti-noise into the ear canal before the original wave can physically pass through that same space. The math of this process begins with a one-dimensional model of superposition, mapping what happens when two coherent waves interact. Focusing on the intersection points of the red and blue sine waves in this graph shows their phase alignment. While this specific 60-degree offset creates a partial reduction, shifting the second wave's phase by exactly 180 degrees perfectly aligns peak with trough, resulting in an amplitude of 0. This presents a question regarding the law of conservation of energy. If the acoustic amplitude drops to 0, the energy cannot simply vanish. In a three-dimensional acoustic field, the energy is displaced. It is reflected back towards its source or diverted into adjacent regions where the waves interfere constructively. ANC hardware spatially engineers localized pockets of zero pressure at the eardrum by increasing sound pressure elsewhere. Predictable sine waves rarely exist in the wild. Environmental noise is stochastic. It is non-stationary and composed of a broad spectrum of constantly shifting frequencies. Digital signal processors cannot directly invert a chaotic, broadband waveform while working in the time domain. The digital processing overhead is simply too high to complete the complex calculation before the sound reaches the ear. Systems overcome this using the fast Fourier transform, or FFT. This algorithm converts the incoming analog noise from the time domain into the frequency domain, unspooling the chaotic noise into a stacked series of uniform sine waves. Once isolated, the component frequencies receive a calculated 180-degree phase shift. An inverse FFT then sums these altered waves back together, converting them into an analog pressure wave for the speaker. The FFT acts as the digital bridge for noise cancellation, allowing microprocessors to parse and manipulate chaotic physical signals in real time. Acoustic environments change instantly. A shifting headphone seal or a tilt of the head alters the internal ear cup geometry, making static filters ineffective. Modern hardware uses closed-loop architecture. An internal error microphone constantly samples sound reaching the user. The LMS algorithm measures this residual noise, updating filter weights. This calculation must account for the secondary path, the converter, amplifier, driver, and air gap, which introduces time lag and phase distortion. The Filtered X LMS protocol solves this by filtering the reference signal through a mathematical estimate of that secondary path, ensuring the phase of the update aligns with the physical sound. Without this correction, the processing lag would misalign the phase inversion, causing the system to function as an amplifier rather than a canceller. Feed-forward topologies use exterior mics to proactively detect ambient noise, while feedback topologies use interior mics to react to what the ear hears. Hybrid ANC integrates both paths. The exterior mic forecasts broad-spectrum noise, while the interior mic refines the cancellation. Despite this optimization, hybrid systems that erase a 500 Hz engine drone will physically fail to block a high-pitched 10,000 Hz siren. The constraint is the geometry of high-frequency waves. A 100 Hz wave is 3.4 meters long, but a 10,000 Hz wave is just 3.4 centimeters, completing a cycle every 0.1 milliseconds. The processor's reaction time often exceeds this window. Arriving late, the anti-noise's shifted phase amplifies the sound. The failure to cancel high frequencies is a hard limit imposed by processing latency and the speed of sound. This necessitates the use of passive isolation materials, like foam and plastic, to absorb the wavelengths that digital algorithms cannot outrun. Removing these low frequencies can trigger a sensation often called eardrum suck, characterized by a feeling of pressure in the inner ear. This is a psychosomatic illusion rather than a physical pressure change. When the ANC system removes the low-frequency acoustic baseline the brain uses to gauge space, it misinterprets the sudden silence as a drop in atmospheric pressure. Traditional FXLMS systems are linear, leaving them vulnerable to the nonlinear distortions caused by small, overdriven speaker drivers. Engineering is now integrating deep learning models to manage these complexities. Specifically, convolutional recurrent networks do not just invert waveforms, they predictively map the complex, nonlinear spectrograms of incoming noise to generate more precise anti-noise shapes. Active noise control has evolved from basic trigonometric phase inversion into a system of predictive neural networks designed to outrun the physical speed of sound.